Okay, so we're going to have another go at lecture 23. There's no way for you to know, but I recorded it once already, and the audio didn't work. So I tested it 3 times this time, and I'm starting to see the value in recording shorter segments. But we'll try again to record the whole lecture, and I'll cross my fingers. If you can hear this, it worked out. Let me remind you of where we were. We were looking at waves in warm plasma, where we do not neglect the effect of pressure anymore, and we express the perturbed pressure in terms of the perturbed density. And the way we did it was to write that P1, where P1, oops, we wrote, if I can write, there we go, P1 over P0, where 1 is the perturbed as usual and 0 is the equilibrium, and I'm going to drop the 0 from equilibrium quantities shortly, is equal to gamma n1 over n0. And this comes from the closure equation that we're using, that P over n to the gamma is a constant. So it's going to be equal to P0 over n to n0 to the gamma. And this is a little bit of a subtle point, perhaps. Well, more than one thing here. Things I've already said. This is what we call a closure. I'm assuming that P over n to the gamma is a constant. This is not what I will call an equation of state. An equation of state relates pressure, density, and temperature. So if I put in an equation of state, I'm not closing my system because I'm trying to solve for the pressure. I'm introducing a new variable, which is the temperature. So I still need one equation. This equation, the closure equation, take the place of the energy equation. And that's what we need to close the system, hence the name. Another thing to notice about this expression is that we're assuming this closure for the stability analysis. We do not need to assume the same closure for the equilibrium. This may be puzzling or confusing or surprising, but in fact, we need something to relate pressure and density when we calculate the equilibrium, and we need the same, in the same way, we need something to relate the pressure and the density when we work on the perturbation, on the stability. The two equations that we introduce for closure, for equilibrium and stability, do not in general need to be the same. We can look at how isothermal perturbation evolves in an otherwise adiabatic plasma, or the other way around. So always keep that in mind. If you don't specify it for the stability, you most likely are going to assume the same thing that you assume for the equilibrium, but you may actually want to stop and be very clear and explicit about how you're doing. Now, I did mention in the last lecture that we can calculate the perturbed density from the continuity equation, or of course, the perturbed continuity equation. And you know what? Let's see how we can do it. Well, let's make a little bit of space here. Our continuity equation says that the partial derivative of the density with respect to time plus the divergence of n times v is equal to 0. Now, I need the linear version of this equation. And remember that the equilibrium velocity was 0. We listed that as one of our assumptions, the simplest assumption, and also that, well, let me type that for prettiness. Oh, come on. Okay, the equilibrium density was a constant. Let me turn this into a subscript. Well, then what we have for our perturbed equation is that the partial derivative of the perturbed density, it's a dot disappeared, that's a divergence, plus, let's see, I don't have a term n0 v0 because v0 is equal to 0. And that would be a 0th order term anyway. Well, let me do it in detail once. So here's all I would have: n0 v0 plus n0 v1 plus n1 v0 plus n1 v1. And all of this is equal to 0. And here I've used that n is equal to n0 plus n1, and v is equal to v0 plus v1. Okay, now this term, the first one is automatically 0 because v0 is 0. The last term is small, and I'm going to throw it away. Then I have a term n1 v0, well, that's also 0. v0 is still 0, regardless of whether it multiplies v1 or sorry, v0 is 0, regardless of whether it multiplies n1 or n0. The only term that's not 0 is this one, but n0 is a constant, so I can take it out of the divergence sign, and I get that dn1 dt plus n0 del dot v1 is equal to 0. And that is my perturbed continuity equation. My next step is to take the Fourier transform in both space and time. Remember how we're doing it. We're using a minus sign for the time variable. So that gives me minus I omega n1 with the subscript f, which may actually decide to drop. And then n0 plus ik with the plus sign dot v1. And all of this is equal to 0. Well, easy to solve for N1. Should be easy enough. Let's see if we can do it without messing up things too much. The i's cancel out. I get the minus sign taken care of. That leaves me with k dot v1 divided by omega times n0. Oops, got an extra plus sign here. So this had a plus sign, but it doesn't, the plus sign is in front. It doesn't mean I have to put in an extra plus sign in there. Sorry about that. And 0. Okay, so this gives me the perturbed density in terms of the equilibrium density. And let me put this in writing. Here we have dropped the subscript f for quantities in Fourier space. That is not unusual. It's a little bit of abuse of notation, maybe a little bit of sloppiness, but it just saves you some trouble. If you're careful, you hopefully will know where you are. That is, in what space you are. If you have any fear of being confused, please do use subscript or some other symbol to distinguish between quantities in Fourier space and in physical space. And the result above allows us to calculate the perturbed pressure in very little work. You remember we have this expression up here. So I just make a substitution and I get that P1 is equal to K dot V1 over omega with a gamma in front times P0. At least this part is fairly simple. Okay, well, that's great, but what were we actually trying to do? I didn't forget because I have notes in front of me, but I feel that at times, maybe often in somewhat lengthy derivations, it's not so hard to get lost and forget where what we're trying to do. We're looking at quantities in warm plasma, where we do not neglect the effect of the pressure. We introduced a perturbation. The plasma is originally unmagnetized and uniform, and we want to find what type of wave is going to appear in this plasma. We've so far worked with the closure equation and the continuity equation. We have not used the momentum equation. And that's what we're going to use to determine the behavior of the wave. And for that reason, our next step is going to be to go back to the momentum equation. Okay, let me just write it down for now, and then we'll work on it. The momentum equation looks like this. I have m and 0 dv1 dt, this is already the perturbed equation, is equal to n0 times q times E1 minus grad P1. This should be pretty obvious, I hope. If you have any doubts, well, we did in detail the density, the continuity equation. You get to this equation in the same way. Okay, now I'm seriously going to drop the subscript for equilibrium quantities. Okay. I moved it and I went too far. Okay. Let me pull it back a little bit. Good enough. Should be readable there. Okay. Now what I'm going to do is take the Fourier transform in space and time. Same as before. You see that this is perhaps not trivial, but once you get the knack of it, there are certain steps that always repeat themselves, not surprisingly. Also, I've not emphasized, this is in general for ions and electrons, so m could be the mass of the ions or the mass of the electrons, and q could be the charge of the ions or the charge of the electrons. We'll elaborate further on this in a moment. But for now, we have m times n. Again, I'm getting rid of the I, of the 0 subscript, and I forgot the I while I was doing that. So here I have minus I omega times V1. Again, I'm not putting subscripts in for quantities in Fourier space. Here I have n times q times C1. And here I have minus grad P that gives me an IK. Okay, so this is going to be a little messy. IK, then I have gamma P0 over omega times K dot B1. And well, that's as good as any way to write this, but let me maybe write it in a more elegant way, minus I omega, let me get that in front, m times n times v1 is equal to n times q times e1, and here the issue is, well, let me write it this way, minus I gamma over omega p0 k to be 1. There is no issue per se, but what I like to do when I write equations is to have the direction is the vector. E1 is itself also a vector as the last term. However, in this case, the unknown is V1, which is dotted with a K, and therefore appears in scalar form by components. And I also like to have, if possible, the unknown as the last term. I can't have both in this case, and that's why I'm writing it this way. But keep in mind, the last term is in the K direction, the previous one is in the E1 direction, and the first one, the one on the left-hand side, is in the V1 direction. That's what we have to work on. There are various things that we can do. First thing that we can actually observe is that if we look at a transverse wave, the pressure is irrelevant. And that's because k dot v1 is equal to 0. That's what transverse means. So that tells us that for transverse waves, we have behavior that we already know. It's the same behavior as we had in the cold case. A wave in a warm plasma, a transverse wave in a warm plasma behaves exactly in the same way as a transverse wave in a cold plasma. Great result, and we need to spend all this time to find out that the modification we did really doesn't matter. Well, it doesn't matter for transverse waves, but that's not the end of the story. Now, as I've mentioned, and let me remind you of it again, we are looking at a system that is unmagnetized. The plasma is unmagnetized. It's uniform. There is the same density and pressure everywhere. What that means, among other things, is that there is no preferential direction in the plasma. When we have straight magnetic field lines, the direction of the magnetic field is direction that is going to behave differently from the direction that's perpendicular to the magnetic field. Here we do not have any preferential direction. That means that we have the freedom to set the axis in any way we like. Well, we always do, but we don't have to worry about setting the axis in a way that's going to make the math more complicated or less intuitive by neglecting a special direction in our plasma, because there isn't one until we put in a perturbation, a wave, and that is what introduces a preferential direction. What I'm trying to say, and that I will now write down, we can pick the axis. And any way we like. And therefore, I'm going to make special choice that k is equal to k z hat, or in components 0, 0, k. And there is no loss of generality here. I'm looking what's the direction of my wave, and I'm going to set the z-axis to be parallel to the wave number. And you may ask, what if the wave number is not in the z-axis? Well, do a transformation of coordinates and set it such that it is. If you really want to make things complicated, you can leave the direction of k arbitrary. You just make this a lot more messy, but you're going to find the same waves. And by rotation of axes, you will end up finding that the waves we're going to describe now are still the waves that you find in your plasma, just written in different coordinates. Now, looking at the momentum equation, we can actually immediately solve for velocities in terms of electric field. We take the three components of the momentum equation, and we obtain perhaps I can I'll just do a little bit of writing. I mean, this is trivial, but just so that we avoid any type of confusion. So minus I omega m times n times Vx is equal to n times q times E1x, and then k dot Ex is 0, and therefore there is the last term doesn't appear, and that is all. Then immediately follows that Vx is going to be equal, just need to divide over, change the sign, which I fix with moving the I to the numerator. Let me write things in order. IQ over omega m, since the n opposite cancels, and Ex, and that should be it, where Ex is E1x. That is one. The y component is identical. I'm not going to redo it. Vy is equal to IQ over omega m times EY. Now the z component has got a little bit more work, so but it's still pretty trivial. Okay, you can't see it anymore. I can make the equation fit in there and still be able to write here. but I can see it, so just trust me that I'm copying it right. Minus I omega m times n times Vz is equal to n times q times Ez minus I gamma over omega P0 K dot V1 times K, scalar K, because that's all there is from the equation on top of the page. But this is just KVZ for the same reason. I can perhaps skip little bit of steps here. If you put all the pieces together, let me take the result from my notes here. We should get that Vz is equal to Q over M times, let's see, Ez on top. That's the only piece that does not contain Vz, divided by minus I omega. Plus I k gamma P0 over n times omega. Make this a square bracket. Okay, IK should have everything, and this needs to be a little bit longer. All right, and I'm sorry, this is K square. Obviously, have two Ks there. Okay, but that's our Z component of the momentum equation, gives us a relation between Vz and Ez. And here are Vx and Vy. Let me just box them all. And now I'm going to introduce another simplifying assumption. So far, we have left everything in general, that is Vx, Vy, Vz could be the velocities of ions or electrons. Now I'm going to assume that the ions don't move. And we'll come back to what happens if the ions move shortly. You may have noticed a pattern. We tend to do that. And then if we do that, if we take the simplification, then we can write our conductivity tensor and the electric tensor easily. As for sigma, I'm going to have 1, 0, 0, 1, all zeros. It's diagonal, which is great. And here I have 1. Try to make something a little more orderly. 1 minus k squared P0 gamma divided by m times n times omega squared. With didn't leave myself space to actually write. I've pulled out bummer, made a mess. Sorry about that. All of this multiplies I times n times q squared divided by omega m. And the electric tensor K is the identity tensor. I prefer to write I, so I'm going to use I. Plus I sigma over epsilon naught omega. Now here, I'm just going to write again the result. What you get is 1 minus, and I'll remind you of the definition shortly, omega plasma over omega square in positions 1, 1, and 2, 2. Of course, the tensor stays diagonal. And here I have something that's a little more messy, 1 minus omega plasma square divided by omega square minus k square p0 gamma over m times n. Okay. Not bad, a pretty monster. What is quite interesting here is that we have dependence on k. There is a dependence on k in this term, which is quite different from what we had in the cold case. So if you set the pressure to 0, you recover the cold case dispersion relation, which is actually always a good thing to check. It occurs to me that I should point out something more. Let's see. Try again. Whew. Spelling today is a real challenge. Maybe I can make where did it go? Panic attack. Q is equal to minus E, the charge of the electron. And sorry, I messed it up again. And omega plasma, let me just call it omega plasma square, is omega plasma electron square. And as you'll remember, that's equal to the density, which is density both the atoms of the electrons, actually E square divided by ME epsilon 0. I should also say now I've messed up the formatting. Mass is the mass of the electrons. Okay, are we getting anywhere? Maybe. Actually, we are. We're almost there. Well, almost somewhere at least. What we're going to do next is look at the longitudinal waves. And I'm going to solve the dispersion relation for longitudinal waves. Already said that transversal waves or transverse waves don't care about the pressure. Well, we better hope, I don't know if we have to hope, but it would be nice that we didn't waste all this work if longitudinal waves did depend on equilibrium pressure, and we'll see in a moment that they do, because what we have to do is set kzz equal to 0. No, capital K. Or just copying from up here, 1 minus all the stuff equal to 0. Minus omega plasma square divided by omega square minus K square P naught gamma over M n equals 0. Multiplying over, I obtain that omega square is going to be equal to omega plasma square plus K square P0 gamma over M times N. And that's my dispersion relation. That is, I find waves that are not just plasma waves and not simply oscillations with the plasma frequency. There's going to be something more that actually depends on the wave number, the second term here. Now, typically we prefer to write these this result in terms of temperature. Then we use the equation of state for an ideal gas. And we write that P0 is equal to N0 T0, or dropping the subscript N times T. I kept the subscript 0 on the pressure here. I said I will drop it. Well, if you hadn't realized it yet, you shouldn't trust me. Okay. But the result is correct. I don't trust me, go check. Okay, so what we get here is omega plasma square plus K. I replace P0 with N times T, N cancels out, and I'm left with gamma T divided by M. Or omega square is equal to omega plasma square plus K square gamma V thermal square, which is the form that we often use, which we could have gotten from the pressure. The pressure of a density over mass density is velocity, not surprisingly. But the preferred way to look at waves in a warm plasma is to occasionally bring in the temperature in the results. Okay, I said this is, let me type it. V sub T is the thermal speed. Now, one thing that is left so far unspecified is the correct value for gamma. You may or may not know, and I'm not going to elaborate because this is fluid dynamics, and that gamma is equal to, let me use capital N plus 2 divided by N. Where that capital N is the number of degrees of freedom. Okay, well then degrees of freedom of what? Well, here we only have electrons moving. How many directions can electrons move? You may argue that the motion of the electrons is one-dimensional. If I make that assumption and I accept that argument, I set n equal to 1 in the equation above, and I find that the correct value for gamma is 3. that is for an adiabatic, one-dimensional motion. Let me perhaps type that. Okay. Then, I should also mention, you can actually derive these waves using a kinetic approach rather than a fluid approach, and you'll get the same result, but you'll have a stronger case. You won't have to do any reasoning. That numerical value 3 will sort of come out more naturally. But again, you can get the correct result using fluid analysis, and with some reasoning, you can also estimate correctly what the value for gamma should be. The dispersion relation above actually has a name. It's not sure it's got two names. Well, one, let me just write it. The dispersion relation above is called, and let me copy the name so I don't mess this up. It's called the Baum-Gross dispersion relation, by the name of the people that first obtained it. And again, for electron plasma waves. Okay, now what happens if we make the system a little more complicated? We have a few minutes left. I think I'll just state some of the results, and we may have to finish this in lecture 24. What I'm going to do next is to consider the case where the ions are also allowed to move. Okay, so what do you do there? You have to work a little bit harder to obtain a relation between the relation between the electric field and the velocity is the same, except that you have two of them now. So you have to combine them to obtain the electric tensor at the end. Then I'm going to leave these as exercise. Oops, sorry. And simply state the result. In particular, the result, again, for transverse waves, nothing will change. For longitudinal waves, I'm going to have the term with the pressure, which is going to have a few more pieces. And I'm going to distinguish between the pressure of the ions and the pressure of the electrons. And I'm going to, of course, to distinguish between the mass of the ions, the mass of the electrons. And then for longitudinal waves, I'm going to have that setting KZZ equal to 0 with the same assumption, that is the same selection of axis. Actually, it's not an assumption. I'm going to choose the z direction as the direction of the wave vector, so that k is the same direction as the case where the ions didn't move. And again, this is completely general. There is no loss of generality by doing that. If I do that, I get the following dispersion relation. Now I'm going to have to distinguish between, as I said, ions and electrons. So let me use the subscript E for ions. No, the other way. E for electrons. Just making sure you're paying attention. Omega square minus, this is the same term that we just had, K square PE times gamma, where gamma is going to be gamma electrons. In general, the two may be different, over ME and E. And then I'm going to have another term that looks pretty much the same, but with a subscript I instead of E. And here I'm going to have omega square minus K square P ion gamma ion over M ion and ion, where quasi-neutrality will typically make me set the densities of the ions and the electrons to be the same, but that is not a requirement. This is valid regardless. In fact, it may be even with quasi-neutrality that the ions are not single charged, and then the density of the ions would be the density of the electrons divided by the charge of the ions. At any rate, so I may have a Z appearing in there. At any rate, and this is equal to 0. You see that this is going to be a second order equation in omega square. I didn't emphasize it here. My equation up here, my Bohm-Gross dispersion relation, is a dispersion relation for omega square. And that is, I'm going to have omega is equal to plus or minus the square root of the right-hand side. How that sign really doesn't matter. It's just going to tell us the direction of the oscillations in time, but it's the same wave. That is to say that what really matters, what we're really trying to calculate, is omega square, not necessarily omega. And if I set omega square to be my variable, since the two denominators are different, I see that this is a second order equation in omega square. Oops. No. Second degree. Not second order. It's a differential equation. Second degree equation. Sorry about that. In omega square. So that's not hard to solve. And it's just going to be a mess. There are various ways to proceed. The brute force, you just solve it and see what you get, and that's what you get. But we may also obtain a good amount of information by making some considerations on the quantities that appear in this equation. In particular, we can observe that omega plasma ions is much smaller than omega plasma electrons. And I may think maybe I can neglect omega plasma ions and let's see what waves I find. Okay, we observe that omega plasma ion is much less omega plasma electrons. Well, I look at my equation up there and say, well, I'm going to neglect omega plasma ions. If I do that, you see that you end up with the same exact equation as we had before. Okay, that's an approximation, but what this is telling me is that I'm going to have two solutions. One of them is going to be approximately the same one as the case where the ions did not move. And I can go see what the actual difference is if I solve this in detail. But the reason why I'm writing it this way is that I want to emphasize, if we do it this way, we first solve the case where only the electrons can move. Then we say, okay, the ions can move too. And we find, okay, we're going to find the same solution as before, just slightly modified, and we're going to find a new solution. And the new solution is what we're going to look at in the next lecture. For now, nothing new, but there is going to be something new to come in lecture 24. Thank you, and I will see you then.